Hello students, in this video we'll be seeing solution for previous year NEET questions. So particularly we are going to focus on the gravitation unit. So before going inside the questions, let us have a statistical analysis about the previous year question papers, like in this particular unit called gravitation, how much percentage of questions were asked from each topics. So if you just have a look at this pie chart, you can see that around 14% of questions were coming from Kepler's law of planetary motion, and 14% were coming from universal law of gravitation, and 22% were coming from acceleration due to gravity, and 13% were coming from gravitational potential, and 17% were coming from escape velocity, and 11% were coming from Earth satellites, and 9% were coming from energy of orbiting satellite. So if you just have a look, this is the past 33 years scenario, and maximum percentage of questions were coming from these three topics mainly. Okay, so it is from acceleration due to gravity, and then from escape velocity, and then from Kepler's law of planetary motion and universal law of gravitation, and then from gravitational potential. And if you just have a look at the last 8 years NEET analysis, a similar kind of pattern is being observed. Again, 10% were coming from Kepler's law of planetary motion, 15% were coming from universal law of gravitation, 25% were coming from acceleration due to gravity, and 25% were coming from gravitational potential, 10% from escape velocity, and 10% from Earth satellites, and 10% from energy of orbiting satellite. So this is what the scenario in the last 8 years. So what I planned is, I thought of making this video and trying to solve all the topics, all the problems which covers all these topics, and I'm also giving some emphasis on these particular topics, which in which more questions were repeatedly coming. So we'll be having more keen interest in solving problems from these particular topics mainly. Okay, so gravitational potential and acceleration to do gravity. So let us first move on with the first question. It is from the Kepler's laws of planetary motion. The figure shows elliptical orbit of a planet M about the sun S. The shaded area SCD is twice the shaded area SAB. If T1 is the time for the planet to move from C to D, and T2 is the time to move from A to B, then. Okay, so they want us to calculate what is the relationship between T1 and T2, and they've given us four options. So here they have given a figure where you can see a planet M is being placed here, and S is the sun, and you know the planets will be revolving around the sun in an elliptical orbit. So here, based on Kepler's law of area of planetary, uh, aerial velocity is a constant, so it will become dA by dt is equal to a constant. So a1 by t1 is equal to a2 by t2. So here what they have given a condition is a1, that is if you see this in this question, the time period from a to b, that is they are making it twice. Okay, so what happens is a1 is equal to a2. If you take this condition, a1 is equal to a2, because here they given it is twice, so 2a2. Automatically what will happen, you can substitute the value of a1 here, so it will become 2a2 by t1 is equal to a2 by t2. So sorry, this is a2, so this a2 and a2 will get cancelled. You will be getting t1 is equal to 2 t2. So this is the relationship between t1 and t2. So it's a very simple concept. You're going to use or apply the Kepler's law of area of planetary, where the aerial velocity is constant, so dA by dt will become constant, and a1 by t1 is equal to a2 by t2. And here, as per the question, they are saying the area is twice, shaded region is twice, so a1 is equal to 2a2, so it's just a mathematical substitution, and you will be getting the final answer as t1 is equal to 2t2. So the correct answer is option number 2. Okay, so let us move on with the next question. A planet moving along an elliptical orbit is closest to the sun at a distance r1 and farthest away at a distance of r2. If v1 and v2 are the linear velocities at these points respectively, then the ratio of v1 and v2 is. So here they are saying like a planet is moving in an elliptical orbit closest to the sun at a distance r1. So the nearest distance is r1 and the farthest distance is r2, and they are telling the v1 and v2 are the linear velocities at these points respectively. Then what will be the ratio of v1 and v2? So we all know that according to the principle of angular momentum conservation, L1 is equal to L2. So you all know L is equal to MRV. Okay, so L is equal to MRV. So L1 will become MR1 V1 and L2 will become MR2 V2. So you'll be getting it as MR1 V1 is equal to MR2 V2, or R1 V1 is equal to R2 V2. So it will become V1 by V2 is equal to R2 by R1. Okay, so the correct answer is the ratio of V1 and V2 will become R2 by R1. So the correct answer is option number 2. So it is also a very simple question. So you are just going to use the principle of angular momentum of conservation, where L1 is equal to L2, and you know the formula for the angle of momentum. So it is L is equal to MRV, so it will become MR1 V1 MR2 V2. So it's a very simple problem. We're just going to substitute here, and you will be getting the ratio of V1 and V2 as R2 by R1. Okay. The next question is, the time period of a geostationary satellite is 24 hours at a height 6 RE. RE is the radius of the Earth from the surface of the Earth. The time period of another satellite whose height is 2.5 RE from surface will be. So here what they are saying is they want us to calculate the time period of a satellite which is at a height of 2.5 RE from the surface of the Earth. Okay, so RE is the radius of the Earth. So here they have given you the value of T1 as 24 hours, and they have given the values of H1 and H2. Okay, so H1 what they have given is they have given the values of H1 as 6 RE and H2 as 2.5 RE. So they want us to calculate the T2. So you are going to apply this Kepler's third law, which is given as T square is directly proportional to R cube, or T square is directly proportional to RE plus H the whole cube. Okay, so here because RE is the radius of the Earth, so you can take it as T2 by T1 is equal to RE plus H2 by RE plus H1. Okay, so the whole power 3 by 2, because the square is going to come this side, it will become power 3 by 2. So we know that H2 is 2.5 RE and H1 is 6 RE. So you are going to substitute that here. T2 by T1 is equal to RE plus 2.5 RE divided by RE plus 6 RE. Okay, so if you just try to solve this, you will be getting 3.5 RE and below 7 RE. So RE and RE will get cancelled. So you will be getting you know the value of T1 is 24. So T2 by 24 is equal to 3.5 divided by 7. Here 3 by 2 will be coming. Okay, so power 3 by 2. So this will become T2 by 24. So this will become 1 by 2, and 1 by 2 power 3 by 2 is 1 by 2 root 2. So if you solve this mathematically, T2 will become 6 root 2 hours. So the time period for another satellite whose height is 2.5 RE from the surface will be 6 root 2 hours. So the correct answer is option number 2. Okay, So let us move on with the next question. From a body weighs 72 newtons on the surface of Earth, what is the gravitational force on it at a height equal to half the radius of the Earth? So here they want us to calculate the gravitational force on it, like at a height equal to the half the radius of the Earth. So here F surface is given by G m m by RE square. So at a height h RE at a height h is equal to RE by 2. So your FH will become G m m by RE plus h the whole square. So which is equal to G m m by RE plus RE by 2 the whole square. So this will become 3 RE. So this will become G m m by 3 by 2 RE the whole square. Okay. So if you solve this, you will be getting it as 4 by 9 into G m m by RE square. So you know this is what F surface. So here they are given the weight as 72 newtons. So this will become 72 newtons. So automatically what will happen is this will become 4 by 9 into 72. So if you solve this, you will be getting it as 32 newtons. So the correct answer is option number 1. The gravitational force acting on it is around 32 newtons. Okay, so let us move on with the next question. So this is just a theoretical question. You are not going to calculate anything. You are going to understand the concept and you are going to answer. Two astronauts are floating in a gravitational free space after having lost contact with their spaceship. So what will happen? So they keep floating at the same distance between them, move towards each other, move away from each other, will become stationary. So we all know that under mutual gravitational force, astronauts move towards each other with a very small acceleration. Okay, so that is when they are floating in a gravitational free space, like after having a contact with their spaceship. We know that under this mutual gravitational force, the astronauts will try to move towards each other with a very small acceleration. So the correct answer will be move towards each other. So you might have also even seen in movies and all, okay, where these astronauts will be coming out of the spaceships, or some accidents takes place in the spaceships, and these astronauts will be floating in the space. Okay, so during that time also you can see they will be traveling at a very small acceleration, and they will be coming towards each other. So that's what happens here. So the correct answer is option number 2, move towards each other. Okay, so let us move on with the next question. Which of the following plots represents the variation of gravitational field on a particle with distance r due to a thin spherical shell of radius r? R is measured from the center of the spherical shell. So for a thin spherical shell where r is greater than r, what happens is F is equal to G m by r square. So for r equal to r, what will happen is F is equal to G m by r square, and for r lesser than r, F will become 0. Okay, so here if you see, the correct answer is option number 3. Okay, so where you can see the value of r decreases. Okay, so this is what exponentially decreases after a constant r value. So this is what the correct option number 3. Okay, so let us move on with the next question. here you can see again a similar kind of graphical question where they are saying starting from the center of the earth having radius r, the variation of g acceleration due to gravity is shown by. So here again acceleration due to gravity g is equal to 4 by 3 pi rho g r. So where r is lesser than or equal to capital R, so g is equal to 4 by 3 pi rho r cube g by r square. So again here r is greater than r. So here if you see, the correct answer is option number 3. Okay. So next we will move on to the next question. A body weighs 200 Newton on the surface of the earth. How much will it weigh halfway down to the center of the earth? Okay, so here they are telling that a body is weighing 200 newtons on the surface of the earth. So what will be its weight halfway down to the center of the earth? So acceleration due to gravity at a depth d, gd, is given by g into 1 minus d by r. Okay, so which is equal to g into 1 minus 1 by 2, because d is equal to r by 2. Okay, so you're going to substitute there. So automatically gd will become g by 2. So weight of the body at a depth d is equal to r by 2 is given by wd is equal to mgd. Okay, so m into g into 2, so which is equal to 1 by 2 into 200, because m value is 200, so you are taking it there 200. So wd will become 100 Newton. So the correct answer is option number 2, 100 newtons. Okay, so let us move on to the next question. What is the depth at which the value of acceleration due to gravity becomes 1 by n times the value that at the surface of the earth? So radius of earth is r. So here value of acceleration due to gravity at the depth d is given by gd is equal to g into 1 minus d by r, or g by n is equal to g into 1 minus d by r. Okay, so 1 minus d by r is equal to 1 by n, or d by r is equal to 1 minus 1 by n. So d by r is equal to n minus 1 by n, or d is equal to r into n minus 1 by n. Okay, so the correct answer is option number 3, d is equal to r n minus 1 by n. Okay, so let us now move on to the next question. Assuming that the gravitational potential energy of an object at infinity is 0, change in potential energy, that is final minus initial, of an object of mass m when taken to a height h from the surface of the earth is given by. So here they want us to calculate the change in potential energy. So potential energy of an object of mass m on the surface of the earth is given by P is equal to minus gmm by r. Okay, and potential energy of the object of mass m at a height h from the surface is given by, this is at a height h from the surface of the earth. Okay, so it is given by gmm by r plus h. Okay, so change in potential energy, so you can take this as p potential energy dash. So change in potential energy is given by, this is change in potential energy. Okay, so this is given by p potential energy, that is the final minus the initial. So this will become minus gmm by R plus H plus GMM by R. Okay, so if you try to solve this, it's just a mathematical process. If you try to solve this, what you will be getting is GMM H divided by R into R plus H. Okay, so the correct option is option number 3, GMM H by R into R plus H. So that is the correct answer for this particular question. So let us now move on to the next question. The work done to raise a mass m from the surface of the earth to a height h which is equal to the radius of the earth is. So here again you will be going to use this same potential energy formula. Initial potential energy of on earth's surface is given by U initial is given by same formula GMM by R, and final potential energy at a height h is equal to R, because they are saying like the height which is equal to the radius of the earth. That's what they have given in the question. Okay, so you will be getting final potential energy in the same way, GMM by R plus H. Okay, it is a similar kind of a question. So work done is given by UF minus UI. So you're going to just substitute that here. Work done is equal to minus GMM by R plus H plus GMM by R. Okay, so if you solve this, you will be getting the equation as GMM by 2R, because you will be having this H, which you can take it as R. So you will be getting it like this, and we all know GM is GR square M. So this will become GR square M by 2R. So this will get cancelled, and you will be getting W as of mgr. Okay, so the correct answer is option number 1. So the work done to raise a mass m from the surface of the earth to a height h which is equal to the radius of the earth is given by half mgr. Okay, so let us now move on to the next question. At what height from the surface of earth the gravitation potential and the value of g are minus 5.4 into 10 power 7 and 6 meter per second square respectively. So take the radius of the earth as 6400 kilometers. So here they are given v is equal to minus gm by r plus h, and g is equal to gm by r plus h square. So taking ratio of both the things, v and g, you will be getting it as r plus h. Okay, so you are going to substitute the values here. So here the value of v is given by 5.4, so they have given minus, but anyway you are going to take the modulus, so it will become 5.4 10 power 7, and g value they have given it as 6, so you are going to put 6 equal to r plus h. Okay, so if you solve this, you will be getting it as 9 into 10 power 6 equal to r plus h. So now you know h value, you can bring it here, and r value is 6400 kilometers. Okay, so you are going to substitute that, so you will be getting the value of h as 2.6 into 10 power 6, or it is 2600 kilometers. Okay, because r value is 6400 kilometers. Just a mathematical substitution. You're going to substitute here and you're going to bring it this side and you're going to subtract it. So it will become 9 minus 6.4 into 10 power 6. So it will become 2.6 into 10 power 6 or 2600 kilometers. So the correct answer is option number 3. Okay, so let us now move on to the next question. The ratio of escape velocity at Earth VE to the escape velocity at a planet VP whose radius and mean density are twice as that of Earth is. So here they are saying find the ratio of the escape velocities. So you can take the escape velocity of Earth VE is equal to r into root of 8 by 3 pi 0. Okay, and similarly you can take the escape velocity for a particular planet. Okay, so if you take the ratio VE by VP is equal to r root of rho divided by rp root of rho p. Okay, because for VP you will be getting it as like this, rp root of 8 by 3 pi g rho p. Okay, so the common terms will get cancel each other if you are taking the ratio. Okay, this will not cancel, sorry, rp will be there, so you'll be getting it like this. Okay, so here they have given rp value as 2r and rho p value as 2 rho, so you're going to just substitute them. So VE by VP is equal to r by 2r into rho by root 2 rho, that's all. So you'll be getting it as 1 by 2 root 2. So the ratio is VE by VP will become 1 by 2 root 2. So the correct answer is option number 4. So it's a very simple substitution of the formula, where you're going to use the escape velocity formula for Earth and you're going to take the escape velocity formula for the particular planet and you're going to take the ratio of it, V by VP. Okay, so it's a very simple problem. So let us focus on the next problem. A black hole is an object whose gravitational field is so strong that even light cannot escape from it. So to what approximate radius would Earth have to be compressed to be a black hole? Okay, so we all know what is a black hole is, which is so strong that light cannot escape from it, it will absorb all the light. So now as per the question, if you see, you are trying to compress the Earth into a very small size. So how much you need to compress, how much radius it should be compressed so that it will become or it will behave like a black hole. Okay, so here again VE is given by root of 2 gm by r, which is equivalent to c. Okay, so r is equal to 2 gm by c square. So you are going to substitute the formulas here, 2 into and g value here they have given, so it is 6.667 into 10 power minus 11 and m value is 5.98 into 10 power 24 divided by 3 into 10 power 8 the whole square. So if you solve this, you will be getting it around 8.86 into 10 power minus 3 meters. So this you can approximate to around 10, because we don't have an option called 10 power minus 3 here, and we can approximately take the value as 10 power minus 2 meters. So the correct answer is option number 2. So the radius of the Earth should be around 10 power minus 2 meters so that it will start behaving like a black hole. Okay, so let us go on with the next question. If you see, all these are all like simple problems, just you are going to make use of the formulas. So before, whenever you're preparing, you just try to take a small piece of paper and write all the formulas which is relevant for the particular topic. So that's what I've given you, the different topics also. Even if you take a gravitation unit, you can see you have around 5 to 6 different topics. So you can just make a heading of all these 5 to 6 topics, and you can write some specific formulas. Okay, from those formulas you can easily try to solve all these problems at a very faster rate. Okay, so you don't have to think so much and all. Just you're going to substitute the formula and you're going to solve. You can see as we solve so many problems, same formulas are being repeated and we are using it in a different manner. Okay, so the next question is, if v is the escape velocity and v0 is the orbital velocity of satellite for orbit close to the earth's surface, then these are related by. So they want us to find out the relationship between the escape velocity and the orbital velocity. Okay, so here the escape velocity v is given by root of 2 gm by r. So where m and r are the mass and radius of the earth respectively. So m is the mass of the earth and r is the radius of the earth respectively. So the orbital velocity of a satellite close to the earth's surface is given by root of gm by r. Okay, so what you want to do, you want to find out the relation, means ultimately you are going to take the ratio of that. So ve by v0 is equal to 2 gm by r divided by 2 gm by r. So this will get cancelled. So ve will become root of 2 v0. Okay, so it's also a very simple problem. The correct answer is option number 3. ve is equal to root of 2 v0. Okay, sorry, not this one, this one, root 2 v0. Okay, so the correct answer is option number 4. Okay, so let us move on to the next question. A remote sensing satellite of Earth revolves in a circular orbit at a height of 0.25 into 10 power 6 meter above the surface of Earth. If Earth's radius is 68 into 10 power 6 meter and the g value is 9.8 meter per second square, then the orbital speed of the satellite is. So here they want us to calculate the orbital speed of the satellite. So it is given by g mm by r square is equal to mv square by r. Okay, so also we know that r is equal to r plus h. Okay, so if you just solve this, you will be getting the v value as v is equal to, because r and r will get cancelled and m will get cancelled, so v will become equal to gm by r. Okay, so again this is equivalent to root of gm r square by r square r, which is equal to root of g by r into r. Okay, so you know the values of g and r and all, so you can substitute it here. V is equal to 9.8 divided by 0.25 into 10 power 6 plus 6.38 into 10 power 6 into 6.38 into 10 power 6. Okay, so if you try to solve this with the help of your calculator or something, you can try to solve this mathematical equation. I'm not going to solve it now. You will be getting it as 7.76 into 10 power 3 meter per second or 7.76 kilometer per second. Okay, so the correct answer is option number 2. The orbital speed of the satellite is around 7.76 kilometer per second. Okay, so let us move on to the next question. A satellite S is moving in an elliptical orbit around the Earth. The mass of the satellite is very small compared to the mass of the Earth. So they have given again some options here, so you're not going to solve anything. So the first option is the acceleration of S is always directed towards the center of the Earth. Second one is the angular momentum of S about the center of the Earth changes in direction but magnitude remains constant. Third one is the total mechanical energy of S varies periodically with time. Fourth one is the linear momentum of S remains constant in magnitude. So you can read the question: a satellite S is moving in an elliptical orbit around the Earth. The mass of the satellite is very small compared to the mass of the Earth. Then what will happen? So here force on the satellite is only gravitational force, so which will be always towards the center of the Earth. Okay, so the acceleration S is always directed towards the center of the Earth, so that is the correct option number 1. Okay, so let us now move on to the next question. So the next question is: the radio of circular orbits of two satellites A and B of the Earth are 4r and r respectively. If the speed of satellite A is 3v, then the speed of satellite B will be. So what they are telling us is, they are saying the two circular orbits, that is the two satellites A and B of circular orbits 4r and r are there, and the speed of satellite A is 3v. What will be the speed of satellite B? They want us to calculate the orbital speed of satellite B. So the orbital speed of satellite around the Earth is given by V is equal to root of gm by r. So V is inversely proportional to r. So Vb by Va will become root of Ra by Rb, or Vb is equal to Va root of Ra by Rb. So here Va they have given us 3v. You can see here in the question they have given us 3v. So Vb is equal to 3v into root of Ra. They have given it as 4r over here in this question, and Rb is r. So 4r by r. So if you cut which is the, so the Vb will become 6v. So the correct answer is option number 2, 6v. So it's a very simple question. Which is making use of the formula V equal to root of gm by r, and V is inversely proportional to 1 by r. So as I was saying earlier, if you just know the formulas, you can easily solve these problems along within a minute. Okay, it will not take more than time, and you will be getting the exact accurate values if you memorize all the formulas correctly. Okay, so the next question is: a satellite of mass m is orbiting the Earth of radius r at a height h from its surface. The total energy of the satellite in terms of g naught, the value of acceleration due to gravity at the Earth's surface is. So here they want us to calculate the total energy of the satellite. Uh, you all know that the total energy of the satellite is given by minus gmm by 2 into r plus h. So here you can multiply r square on the numerator and the denominator. Okay, r square by r square. If you multiply, you will be getting total energy as minus gmm r square by 2 into r plus h into r square. Okay, so you all know that g naught is given by gm by r square. Okay, so this term will become g naught. So the total energy will become minus g naught m r square divided by 2 into r plus h. So the correct answer is option number 3, minus mg naught r square by 2 into r plus h. Okay, so that is the correct answer, option number 3. So let us move on to the next question. The additional kinetic energy to be provided to a satellite of mass m revolving around a planet of mass m, capital M, to transfer it from the circular orbit of radius r1 to another radius r2, where r2 is greater than r1. So here again they want us to calculate the kinetic energy, the total kinetic energy, where the total kinetic energy is given by k kinetic energy final minus kinetic energy initial. Okay, so del Ke is again given by minus of gmm by 2r2 minus of gmm by 2r1. Okay, so this will become gmm by 2 into 1 by r1 minus r2. Okay, so it's also a mere substitution of the formula. You are going to take the difference of the kinetic energy final and the kinetic energy initial. So the kinetic energy final is gmm by 2r2 and initial is gmm by 2r1, because they are given the radius of the circular orbit as r1 and another radius as r2. You're going to substitute and you're going to take the common terms outside. So if you see here, the correct answer is option number 2, gmm into 1 by r1 minus 1 by r2. Okay, so I think this video would have been useful for you people to understand how to solve the various problems which are related with the gravitation unit. And as I was saying, you try to make take a piece of paper and separate the topics. Okay, as I showed in the first slide, the 6 or 7 topics, you write their names and try to write the formulas which are relevant to those particular topics. So if you remember all these formulas, you can easily understand the question. As you read the question itself, you'll be able to understand it, and you're just going to substitute those formulas there directly and you're going to find the solution. So it will be very easy, just mere substitution of the formulas. You can see all these problems whichever I'm trying to solve is not having more than 3 or 4 steps. Okay, you can easily solve it by just substituting the formulas. Okay, so I think this video will be useful for you. So prepare well for your exams and I wish you good luck for you. Thank you.